In this video, we'll focus on the cardioid. Now, we've already seen one example. We'll look at a couple more examples in this video. Notice that the equation for a cardioid can be written as r equals a times 1 plus cosine theta, r equals a times 1 minus cosine theta, or we could use sine. R equals a times 1 plus sine theta, and r equals a times 1 minus sine theta. Now do note that a must be positive here, and it's going to pass through the pole. An alternate way that you may see these equations is, rather than in the factored form, we could distribute the a. So just do be aware you may see them as a plus a cosine theta, r equals a minus a cosine theta, r equals a plus a sine theta, and r equals a minus a sine theta. Same thing, they're still cardioids, we just have the a distributed through the parentheses. So let's look at an example, and again, we're going to focus on using technology to help us sketch these. In the calculator, we first want to make sure we have the correct mode. So radians is what we need, and polar is what we need. So when we go to y equals, it's actually r equals. It's in the polar mode now. We'll just type in the equation, 3 plus 3 sine theta. If you want, we can close that parenthesis, and I'm going to hit graph. Now, my graph is a little different because I've played with the window a little bit. I'm going to hit zoom 6 to standardize the window. And from here, we're going to change the scale a little bit so that we can make it fit the window a little better. So it looks like the y min is, say, -3. Y max is 1, 2, 3, 4, 5, 6. Theta min, typically I like -2 pi. And go to 2 pi, which is already there. The x, let's make that, I think -5 would be about right. The x max +5. Y min, I think -2 if I remember correctly would work. And y max, I think it went up to around 5. So I'm just going to go to 7, a little bit higher, and get the graph. And so here we have a little bit better picture. It's still skewed due to the rectangular window. So if we wanted to, again, square that window, we could hit zoom 5 to square that window. And now it looks a little better. We have the cardioid. Now, in order to get some points, there's some tricks that we can use to get some points that we can then plot on our paper. One thing to do is we can go to second zoom, which will take us to the format. And we want to turn the polar GC on. So I'm going to go right to polar GC and hit enter. Next, you want to hit second trace, and then number 1, we want to choose values for theta. So at this point, we can type in different values for theta. Let's say, what if theta is on the polar axis? Theta is 0. It's going to give us a value of 3, which makes sense. It looks like it's on 3. So let's plot that. We have 1, 2, 3 on the polar axis. And we could get some other values. Another good one may be pi halves. So second trace number 1. Let's say theta is pi halves. Let's type that in there correctly. And it gives us 6. R is 6. So 1, 2, 3, 4, 5. A little bit off the grid. That's okay. We're up here. And we can do some more. Let's say second trace value. Let's say we wanted to know what's happening at pi. It looks like it's symmetric, so pi is probably going to be at -3. Let's see if that's true. Let's type in pi for theta. And it looks like the r is 3, which is over here on the negative side. And we could continue doing this. We could get more and more points as needed, but I think we have enough for now. So we're going to have this curve. It's going to go through the points, go up to the pole, and again curve back around, trying to make it look symmetric about the angle pi halves or the y-axis. So there we have the graph of this cardioid. And just as a reminder, another way to write this one would have been, we could factor out the 3 and we would have 1 plus sine theta. Sometimes we see it in the distributed form, sometimes it's factored. Notice in the next example it is factored. So in the next example we will begin again with putting it into the calculator. Go to y equals, we'll clear out what's already there, and we can type in the equation. Notice an alternate way to write it is we could have distributed the 2. We don't need to for the graph, but we could. And let's just hit graph. It's set to the previous settings, which we'll need to change. Here we have the cardioid, but let's change the window a bit to make it look a little neater. Looks like I need to make my y min go down to maybe -3 and the y max to go up to +3. So window, y min, let's make it go to -3, and the y max, what did I say, 3, +3? Forgot already. Graph. And here we have a graph. Let's zoom 5 to make it a little more square. And we have the cardioid. Again, to get some points to plot, we could go to second trace and choose some values for theta. It looks like at 0 it's at the pole. We could confirm that, and it is. So we know at the pole we have a point. We could see what's happening at pi halves. Second trace number 1. Let's see what's happening at pi halves. So on the y-axis we have 2, and that looks about right. So 2. Looks like we have symmetry about the polar axis. So down here we're going to have another 2. We could confirm that by, again, using the function. I'm going to go over here to the value again and see what's happening at the angle pi. It looks like we have 1, 2, 3, 4. Let's double check that. Enter, and indeed we get 4 units away from the pole. 1, 2, 3, 4. So we have a point here. And from here we can again sketch the graph of the cardioid. A little wobbly there. It's certainly not perfect, but we have a quick sketch. We could certainly make it more accurate by getting more values, so we could test other angles to see what the value for r would be and get some more points. But for now we're just getting a very rough sketch of the cardioid. So that is the graph of 2 different cardioids. Notice that these do touch the pole. A cardioid is going to touch the pole. We'll see another graph in the next video that looks similar sometimes, but it doesn't actually touch the pole necessarily.